Welcome to This Explainer. Today, we're unpacking the ultimate statistical toolkit for transforming raw, messy data into rock-solid conclusions. And don't worry, we're going to do it without getting completely lost in the math. If you've ever wondered how scientists, economists, or social researchers move from a simple hunch to a proving fact, you are definitely in the right place. We're going to break down the exact journey every researcher takes to uncover the truth. Here's our roadmap for today. First, formulating a hypothesis. Then, the steps to actually test it. After that, we'll weigh parametric versus non-parametric tests, dive into understanding correlation, and wrap up with predicting the future using regression. All right, part 1, formulating a hypothesis, the starting point. Every massive discovery, it all starts with one hyper-focused question. Basically, your hypothesis is the compass for your whole investigation. It's not just some random wild guess. It's a clear, testable statement predicting how different variables relate to each other. And honestly, the golden rule here is simple. If you can't test it, it's not a valid hypothesis. Now, in the stats world, this actually splits into two competing claims. You've got the null hypothesis, H0. Think of this as the status quo, or the default assumption. It's the ultimate skeptic saying, nope, nothing to see here, no relationship exists. On the flip side is the alternative hypothesis, or H1. That's the exciting relationship we're actually hoping to prove. Our whole goal in research is usually to scrape together enough hard evidence to reject that boring null hypothesis. But you don't just wake up one morning with the perfect hypothesis, right? There's a systematic 8-step process to get there. You start way up top by identifying a broad research problem, reviewing the literature, and defining your variables. Then you funnel it down. You make sure it's testable, you check its scope, and you keep refining it until you've got this highly specific, formal hypothesis that is totally ready for the lab or the field. Moving on to part 2, steps to test hypotheses, putting it to the test. Okay, so we have our formal hypothesis. Now we shift gears from scientific philosophy over to the actual statistical mechanics. We're using sample data to make big inferences about an entire population. This testing life cycle moves logically. We set our initial parameters, stating H0 and H1, and decide on our significance level, which is basically our threshold for evidence. Then comes the heavy lifting, collecting the data, calculating a test statistic, finding the p-value, and finally making a definitive decision. But here's the catch. Whenever we draw a conclusion from sample data, there is a very real risk that we could just be wrong. If we reject a null hypothesis that was actually true, that's a type 1 error. Think of it as a false alarm. But if we accept a false null hypothesis, that's a type 2 error, kind of like sleeping through a real fire alarm. Believe it or not, the entire field of statistics is practically built to minimize those two specific errors. So how do we actually make the call? Well, it all boils down to the p-value. This little number tells us the probability of seeing our data if the null hypothesis were actually true. If that p-value falls below our alpha limit, which we usually set at 0.05 or just a 5% chance, boom, we have enough mathematical evidence to finally reject the null hypothesis and claim it genuine discovery. Next up, part 3, parametric versus non-parametric tests, choosing your path. Now that we know how to test, we hit a major fork in the road, parametric versus non-parametric tests. Parametric tests, they are incredibly powerful, but man, they are rigid. They need a normal distribution, that classic bell curve, and they work with continuous, highly measurable data. Non-parametric tests, though, are your flexible, distribution-free alternatives. They're an absolute lifesaver when your data is messy, skewed, relies on simple rankings, or if you're just working with a super small sample size. Let's zoom in on just how demanding those parametric tests really are. If you want their high-level precision, your data has to strictly meet 4 criteria. First, it's got to be normally distributed. Second, the variance within your groups must be roughly equal. We call that homogeneity of variance. Third, your observations have to be completely independent. And fourth, the data must be measured on an interval or ratio scale. Seriously, if you violate these assumptions, your parametric test is going to confidently hand you a completely incorrect conclusion. Let's ground this in reality. Say you want to compare the average test scores of 2 totally independent classrooms. If your data is beautifully normal and hits all those strict assumptions we just talked about, you go with the parametric independent samples t-test. But If those scores are highly skewed or you've only got a tiny handful of students, you'll immediately pivot to its non-parametric twin, the Mann-Whitney U-test. It's the exact same goal, you're just using a different tool based on the shape of your data. All right, part 4. Understanding correlation, connecting the dots. Up to this point, we've mostly looked at testing differences between separate groups. Now, we're evolving our approach to explore continuous relationships. Correlation is just a beautiful concept. It quantifies how changes in one variable are associated with changes in another. Like, as the number of hours you study goes up, does your final test score go up too? Correlation measures exactly that, both the strength and the direction of that relationship. And the best part is, it uses a really simple, standardized scale. We're talking about the Pearson correlation coefficient, usually just called R. It ranges from +1 to -1. A score of +1 is a perfect positive relationship. One goes up, the other goes up exactly in step. A score of -1 is a perfect negative relationship. One goes up, the other goes down. And a score dead in the middle at 0, that means absolutely no linear relationship exists whatsoever. Now, I know the formula for this can look a little intimidating at first glance, but really, don't panic. The crucial takeaway is just the final result. By plugging a sample set of students' study hours and test scores into this calculation, it spits out a perfect one. We've mathematically proven that, in this specific case, higher study hours perfectly and reliably correlate with higher test scores. To put that into perspective, what does a correlation of 0 actually look like in the real world? Well, if your variables yield a 0 correlation, changes in one absolutely do not predict changes in the other. They are as completely and totally unrelated as a person's shoe size and their level of intelligence. Knowing someone rocks a size 12 sneaker tells you literally nothing about their IQ. Finally, part 5, predicting with regression. Predicting the unknown. For the last leg of our journey, we take those relationships we just proved with correlation, and we use them to predict the future. While correlation just tells us if two things move together, regression analysis is our ultimate predictive framework. We can use simple linear regression to predict an outcome based on just one factor, or we can use multiple linear regression to forecast outcomes based on a whole complex web of variables, which is exactly how massive businesses forecast their sales based on ad spend, seasonality, and market trends all at the exact same time. Wow, we've covered a ton of ground today. We've seen firsthand how this statistical toolkit, from t-tests all the way to regression, is incredibly powerful for dissecting data and uncovering the truth. But I want to leave you with one final, absolutely crucial thought. No amount of sophisticated math can save a poorly conceived idea. The validity of your entire journey and literally every calculation you make ultimately depends on the quality of that very first hypothesis. So before you crunch the numbers, you have to ask yourself, are you asking a question worth answering? Thanks so much for joining me on this explainer, and keep asking great questions.